É,
Okay, I think shall we? Well, there is more people coming, I believe. I already shouted outside, but I think we can continue for. Uh, it's on. It is. It's on. Okay. So well, today now we're gonna have a presentation for Yara Gobato from University of São Carlos in Brazil. As she said, she was mentioned that it was not could be a little bit outside from Magnus, but Magnus is there. Exiton coupling with the Magnum, very looking forward for that. But let's see. I hope that will be fun.
this is true.
Yeah, that's true. Okay, good to know. Good to know. But involving bidimensional materials, van der Waals, structures, that should be very interesting for all. So please, Yara,
Okay.
thank you.
So thank you very much for the opportunity. Thank you for eggs and this place. What I learned a lot, Carlos. Carlos eggs. I always call him eggs. and and the title is on purpose because he asked me to put Magno there. Actually, there is Magno in the story, but it's not about Magno work. Okay, so this work is a successful collaboration among different institutions, from my university with my students, and from CNPN. Ingrid is here, my collaborator. She's responsible to make samples, and Alison Cador as well. And this work I'm going to present, it started with this collaboration with Delft University, because I had a sprint FAPES project, and we started to work together. And afterward, I started to work with Florian Dingberger, which is a specialist of this material. And also, as there was some single photon emitters in my samples, so I also have a sprint in quantum technology, so single photos with this group. And of course, with the theoretician to help to understand what's going on this type of structure. The main work is to know what happens when you put a magnetic material with semiconductor material with another semiconductor material that is non-magnetic. What is going on? What can modify excitonic and Valley properties of TMD, which is transition metal dicocogenide material. So I will explain better. And it's not only proximity effects, there are other effects which I'm going to explain. So as my talk is completely different from the subject it's going on here, so I will present some basic concepts about 2D materials, which are non-magnet, such as monolayer transition metal dicocogenide materials, which are semiconductor materials. And after, I will focus on this special material, which has very different properties as compared to other 2D magnet materials. And also, I will talk a little bit about what can affect the Valley and the exon properties, magnet proximity effect, charge transfer, because we are dealing with two semiconductor materials. We have a band alignment, so we can have charge transfer, which is spin, cannot spin, it can go with a specific spin if it's ferromagnetic phase. And more recent, I discovered that there is another effect that can play and change things, which is resonant energy transfer. Okay, and so basically, you present results of these two heterostructure. We start with this one, which is more simple, and a more complicated one that is at the end of my presentation. So first, I would like to say, where is São Carlos? I'm from São Carlos, the same city than Carlos Eggs, is in the state of São Paulo. So we have two universities, mine and USP, that is University of Carlos. Mine is very beautiful place. You can visit, much beautiful than USP, because it was a farm that was a very green campus as compared to USP. So, no, okay. So my presentation is about these 2D materials, van der Waals materials, which is very easy to prepare. Ingrid do not agree, but you just buy crystals, or you have a collaborator that grow crystals, and you can exfoliate, because you have the van der Waals interaction between the planes, so you can exfoliate very easily, and you can have monolayer, 2 layers, or 3 layers. These are the image, optical image, and you can combine them to have heterostructures, and this is made in CNPN in Campinas by Ingrid, that is here. So this, I would like to show before to start, the facility we have to perform this work. So in some cases we have also a standard micro PL set up to do characterization of the samples. So it's a homemade system. And we also have a new multi-user equipment where you can do Raman as function of temperature. So you can probe phase transition when you have a 2D magnet, for example. And with different lasers, we can control polarization. And you can also observe magnons if you use low frequency Raman. It depends on the sample. Okay, so it is a free, everybody can use, just you can book and use the system. It's a commercial system of VTech. And we also have FAPESP in state of São Paulo has several grants with multi-user equipment. So you have the equipment, you have to share with others. So I have get another one that's with a cryostat, Montana cryostat, where I have small fields. And I can do photoluminescence with a spectrometer, and I can also investigate single photometers with a specific configuration. And when I need higher field, we also have a system there. You just have to pay to use. It's an AtoCube system where you can have magnetic field up to 9 Tesla, low vibration, because 2D materials needs low vibration. So it's very useful for several works that I have performed in the last few years. So this is, when I need more field, I'm used to go to Nijmegen in Netherlands. I can use 30 Tesla, which I like to show to the theoretician. It's a resistive system. This is me and my student there. And if you need 30 Tesla, you need 36,000 ampere. So it's very expensive. So you have to apply for a grant, and you have a specific system, which is not, it's very, very expensive. So few projects are approved in these systems. So I'm dealing about, I work with van der Waals materials. Most of you are used, but a specific group, transition metal diconcave materials, because they are semiconductor materials. And when they are monolayer, they have direct gaps. So it's good to emit light from visible to near infrared. And you can combine with other materials, such as magnetic materials, and have unique properties. You can modify properties of, it's a new system. And you can also twist, because these changes of valley and X property can depend on the twist angle between the layers. And you can make devices and investigate. You can apply gate, doping, electrical field, which can modify, for example, magnetic properties of these 2D magnetic materials. And so GMDs have hexagonal crystal structures. When you have bulk, it's undirect gap semiconductor material, so it's not nice. The PL photoluminescence is very low. On the other hand, if you have a monolayer, it's a direct gap semiconductor material, so a strong emission of light. And in addition, so you can have a very good system to measure photoluminescence. In addition, it has a strong bind energy of excitons as compared to, for example, with 3,5 semiconductor materials. The bind energy is 10 millielectron volts. If in 2D is 300 millielectron volts, so on room temperature, you have an exciton, so it's very strong, and it's a very nice system to investigate, for example, excitons, tryons, when you have 2 electrons and a hole bind with Coulomb interactions. So it's a very nice system to investigate exciton complexes. And furthermore, it has very nice Wiley properties, because there is this broken inverse symmetry and strong spin-orb coupling, so you have a spin valley locking, so which means that the optical transition involves circular polarized light. The direct gap are on the corner of the hexagon of the first Brillouin zone, but they are degenerated, but they are not equivalent in terms of spin. So you can select one value if you use circular polarized light, or another value. It's the same gap, but different. They are not equivalent. And furthermore, in this transition metal dicogonal materials, we have two types. Two groups. One group we call bright material, because for the selection rule, you need conservation of spin and a conservation of momentum. And the fundamental transition is spin allowed. And there is another group. So, and when you measure PL, we have an exton and a trion in different energies. And there is another group that the fundamental transition is spin forbidden, because you change the spin of the bands. And these materials are called dark materials. Of course, you can have these dark extons if you have other things to do, but it's another selection rules. And you can do photoluminescence and have several peaks, which are related to different exciton complex. And you can resolve, but you need very good samples. So that's for this reason, I'm always asking Ingrid to very good samples. So what happens when you apply perpendicular magnetic field? When you apply perpendicular magnetic field, I mentioned that the valleys are degenerated. You break the valley degenerescence, which means that the gap here in B0 is the same, but when you apply perpendicular magnetic field, the gap from one valley and another valley are different. And so you can measure, as you can measure circular polarized photoluminescence, you can measure sigma plus and sigma minus, sorry. And you can measure the G, valley G, we call this difference of energy of the valleys are proportional to the magnetic field, and you can extract the G factors, which we call valley G factors, and it depends on the spin and the orbital angular momentum, and for bright extons is around -4. But if you are dealing with dark extons, it can be -9. So it depends on the bands involved on the optical transitions. And people are used to measure, so the emission, circular polarized emission, sigma plus, sigma minus, and the difference of energy you plot, which is energy splitting as function of magnetic field, and you can extract these G factors. So this is important for me because I want to know what happens with these valley properties and with exciton properties when you have these magnetic substrates. So before, as you know, there are different types of 2D magnet materials. Some of them are difficult to work because they are not stable on air. You need a glove box to prepare them. But some of them are very stable, such as CR-SBR, that is the one I start to work. There is another one that I'm working also is CRPS4, because I have this collaboration with people from DEFT, and they are also working with this material. But these 2D magnet materials, they are very interesting. They have different properties. They can have easy magnetization on the plane or perpendicular, or the magnet properties can depend on the number of layers. For example, for this material, the magnetization is perpendicular. If you have one layer, it's ferromagnetic, 2 layers, antiferromagnetic, and so on. And you can modify these magnet properties if you have, for example, strain. You can use a strain cell and just apply strain. It's antiferromagnetic. With strain, it can become ferromagnetic. And you can also make a device, apply gates. You can have a doping and electric field. In this, you have an engineer to modify magnet properties in this 2D magnet material. So it's a very rich system, but it's better to have a material that is stable on air, which is much easier to prepare. So just to review properties of this CR-SBR, when you exfoliate, you have this shape of flakes, And you can identify the crystal axis. A is the longer here, and B is the smaller. And it's an isotropic material. It has orthorhombic structure. And if you look from the bond structure, you can see that it's very anisotropic. And you can probe this anisotropy by using photoluminescence. For example, if you excite with linear polarized light and detector linear polarized light with different angles, so you can see that the emission is only when excited on the B axis, and there is no emission on the A axis. And this anisotropy is for optical properties, but also for magnetic properties. It's very anisotropic material. So, for example, just to show, okay, this is the magnetic. If you look in the A axis, B axis, or C axis, the phase transition occurs. Well, the temperature is the same, the Néel temperature, but the properties, magnetic properties, are not equivalent in different directions. And for optics, you can see, you can measure reflectance or PL, as I show you. You only observe PL when the linear polarized light is on the B axis.
Just a quick question. In that flake that you show, what's the size of the...
The typical size is 10 micro. Yes, that's for this reason you need micro PL and low vibration. So it's necessary this type of infrastructure. Because if you put a laser, if it's moving, you're not... For transport measurement, it's not a problem. But for optics, you need low vibration systems. And there is two-phase transition in this material. One is the Néel transition, but people observe also another transition, which is on discussion, but it's more related to defects in the crystals. And you can, and the magnetic, there is a strong coupling between exciton properties and the magnetic order. We see in other slides this more clearly. But if you plot, for example, the emission as function of temperature, this is the color code map of the photoluminescence, you can see clear changes on the Néel temperature, and in our case, we can always see near change on this phase transition related to the defects. So in this material, it's very special. I will explain why this occurs, but the exciton is coupled with magnetic order, and you have magnon coupled with exciton, you have polaritons coupled with magnetic properties. There are really special properties that you cannot find in other materials. So I forgot to mention that it's antiferromagnetic material, because sometimes I forgot things, and A-type, and the Néel temperature is 132 for bulk material. If you exfoliate and you have few layers, you decrease the Néel temperature. So here, still the magnetic properties, as I mentioned, is an anisotropic. So if you apply on the easy axis, which is the B axis, you can apply field, and you can align the magnetic moment, the spins, and you have a spin flip around 0.3 for a few layers. And for if you apply magnetic field on the A axis, you need 1 Tesla to have this spin canting. And if you apply perpendicular magnetic field, you need a higher field. So that's for the reason sometimes I need this AtoCube system. Okay. So this, I will call CRSBR CSB, because it's much easier to pronounce, CSB. And it has a strong coupling between its electric and magnetic and optical properties. And why? It means that you can use the exciton as a sensor of the magnetic phase, because the energy of the exciton depends if it is in ferromagnetic or antiferromagnetic phase. Why? Because it's the main explanation, qualitative explanation, is because when you shine light, for example, so you have the exciton in one layer, and you cannot have diffusion because the spin here is different. And when you have phase transition, it's ferromagnetic, you can have interlay hybridization, because you can have diffusion of electrons from one layer to another layer. So, and this hybridization here, that can occurs when you have the magnetic phase, ferromagnetic phase, change the bond structure, which means here is easier to see. Due to this interlayer hybridization, the gap for antiferromagnetic phase and for ferromagnetic phase are different. If the gap are different, the exton energy is different. So I can use the exton, which is very easy to measure. You can use the exton from photoluminescence to probe the phase transition.
So now you're placing the TMD on top of this
Not yet.
Not yet?
Now I'm just doing some revision about these properties, because when I put the TMD, this is important to know. I just would like to say that the gap of CRSBR depends on the magnet order. If it's ferromagnet, it's higher energy, and if it's antiferromagnet, it's antiferromagnetic higher energy, ferromagnetic lower energy. The gap, this is an unusual property. Only this, I think only this material has this property. You can change the gap with the magnet order.
Okay. So this is this.
For example, here
this pertains to the physics of the substrate still.
Still.
Okay.
For example, you can see clear here absorbance. You can see the energy is different for the two phases, and if you measure PL, you see the different energy for ferromagnetic and antiferromagnetic phase. You can see clear here. I forgot to mention that the monolayer is ferromagnetic, and this interlayer couplet makes them antiferromagnetic. So if you have a monolayer, if you apply magnetic field, the extra energy does not change because it's ferromagnetic. In plane. Here, sorry, it's B parallel to B. Okay, I forgot. And it can be in plane B parallel to A. You have a spin canting and the saturation field around. It depends on number of layers. For 2 layers, is around 1 Tesla. If you apply for a bilayer parallel to B, it's antiferromagnetic. You will increase the field. You have a spin flip and become ferromagnetic. Very low field. Here it's I think 0.1 more or less, but it depends if bulk is 0.3 Tesla. And you apply parallel field aligned with the B axis, which is the ease axis. If you apply perpendicular, so you need more field to align to have this spin canting up to the saturation field. So you have we can say ferromagnet induced by magnetic field, ferromagnetic state induced by magnetic field. And this is optics. So it's very easy to measure. You just need to have a possibility to measure photoluminescence. And you can probe the photoluminescence, can probe the phase state of the material. It's an advantage because sometimes it's hard to measure a flake. The squid is not possible, so we need mock, other techniques, and so let's go. And as there is this conference is about a magnon, I put 2 slides about magnon, which is not my work. So I just explained that you have this hybridization that appears when you have ferromagnetic order. If you so you have magnons in this system. The magnon is very coupled with extons in this system. So the magnons can modulate the energy of extons because of this property that I just explained. So people can show this by using pump probe technique, which means you can use a laser, pulse a laser to modify your material, and you can probe, for example, reflectivity of the material after to modify it, and you can show and you can control the delay between the pump and the probe, and you can show there's oscillations. You can modulate the energy of extons, and the frequency of this oscillation are the frequency of magnons. So because of this property, it's a special material. It's not only all material that you can use this. So you can measure the frequency. It's exactly the frequency of magnons in this system. So it's a very nice system where exons are coupled with coherent magnons. Okay. And it's also interesting, this material, because even you don't need cavity. As there is this large dielectric mismatch between the material and the interface, you can have polaritons, that is exon coupled with light. And these polaritons are sensitive, are coupled with magnetic properties as well. You can measure polarity and show this phase transition just looking by polaritons in this material. So it's very interesting system to investigate polaritons. And so now, sorry for the time, but it was necessary to have this background. Now I would like to answer the following question. What are the changes that I can observe in the excitonic and value properties of TMD when I combine TMD with a 2D magnetic material, particularly with CRSBR or CSB? And what are the contributions that can be responsible to change these properties? Can be magnons, magnetic proximity effects, and can be charge transfer, and also more recently we discovered that energy transfer is also an important effect. So proximity effect, let's review. There are some works, previous works about proximity effect, but most of the works were performed with magnetic materials that have magnetization perpendicular. Because only perpendicular magnetization can break the Weyl degenerescence. You need perpendicular magnetization. And this is similar magnetic field that you can have a splitting at 0 Tesla, which is very interesting. You don't need a cube magnet that it's very expensive. So people have shown that there's few works, but there are some works. For example, for this material, this material is not stable on air, so it's you have to encapsulate because there are degradation. And people have even probed because there's a hot discussion about magnetic proximity effect. People say only interface is important. But here they show that you can have magnetic proximity effect for the second layer as well. Because this material, if it's mono, is one, for example, for 3 layer is ferromagnetic. For 2 layers is antiferromagnetic. And they can show that they can see other layers. It's not only the interface. The interface is ferromagnetic. So they have shown this work in 5 years ago. And there is this discussion. But most of works, nobody has studied these heterostructures with antiferromagnetic materials. And when I decided to do this, people said, you are crazy. But I was interested to investigate. There is a question.
Quick question, Yara. So it's very evident that this exciton couples to the magnum. And it's like very nice to see that this excitonic energy is very far from the bulk bands. Mm-hmm. And like first question is this just because the wave function penetrates on the dielectric function of vacuum, which is kind of like smaller?
You are asking about the other slide about the pump probe measurements?
No, just like I just wanted to understand why the excitonic energy is so far from the conduction band. Because if you think about like...
they are so far.
Yeah.
But the exciton can probe the magnum not because of the energies. It's because of this hybridization that is sensitive to the if it's ferromagnetic or antiferromagnetic.
Right.
And so this can change because you have this spin canting effect.
Right, but like for instance, if your binding energy is super close to the conduction band, you would barely be able to resolve the excitonic.
Yes, but it's not okay.
And here it's like it's very isolated,
yes,
so you can resolve like many peaks. So I was just wondering if this is like solely character of like the 2D materials, and with the wave function extending perhaps through the vacuum, which would make the excitonic energy.
I think this effect in this case specific is not for all 2D materials. It's only for this material.
Okay.
Because of this property. it has.
Okay, and the second quick question that I had regards the coupling mechanism between magnon and exciton is just like simple magnetoelastic.
I don't
coupling?
know the models that you use. There's some experimental evidence because they show that they can see the frequency of magnon and they test several measurements to prove that it was magnon and exciton. But it's not my work. I look the paper. They prove, and there is not only this paper. There are other. They put the strain and they check everything that prove that the exciton. But the mechanism I don't know.
Okay, thank you.
Okay. Sorry. Yes. And so I decided, as I was in collaboration with Professor Harry van der Zandt, so he was working with this material, he had the crystals. So we decided to make the sample of CRSBR that has magnetization on the plane, and we put a flake of MOS2. And we were not expecting that we had this break of degenerescence, but we decided to measure. And the first thing that we observed that there is some calculation that the bond alignment between these two both are semiconductor materials are very unusual. It's a type 3 bond alignment, which is not usual for. So which means that the charge transfer is very efficient in this type of heterostructure. So here is my flake, so of CRSBR, the crystal axis, and I put few layers of MOS2. So if you measure the emission, so this is the emission from MOS2, which is very separate for the emission of CRSBR. And so just the calculation that they perform calculation to show that it's type 3, that the charge transfer is very efficient. And also because we changed the doping. Usually MS2 is N-type, due to this charge transfer is P-type doping because of this bond alignment. So what happens? So the first thing here is about magnons. Usually, for example, if you measure the temperature dependence of this 2D magnet material, so you have some signatures of phase transition, the first one L and the other relate to defects. And for TMDs, the semiconductors that are non-magnetic, if you change the temperature, you change the band gap as function of temperature. And the band gap change, so here is MS2 on silicon oxide normally, but if it is on the magnet material, strange things appears. The separation, there's a anomalous change of the separation between X and trions, which means we change the trion bind energy.
Sorry, could you clarify? So, which are of these pictures for the bulk and which are for few layers?
Okay.
Because that's probably
here is bulk.
Okay.
CSB is bulk.
Okay.
But here is monolayer MOS2.
Okay.
Because the 2 layers, 3 layers, it's indirect gap, so I don't have PL. Okay.
Okay.
So it's monolayer MS2 on bulk CRSBR.
Okay.
Okay. And I was saying that the separation between X and trion should not change, because I only change the band gap with temperature. So the trion bind energy should not change, which is true for MS2 on silicon oxide. But if I put MS2 monolayer on CRSBR, when there is phase transition, the separation of X and trion change, which is the trion bind energy. You can see clear here. On silicon oxide is constant with temperature. When you are looking the separation between X and trion, which is trion bind energy as function of temperature, there is a change at L temperature. It's a very important change, and it's not a small effect, it's then a change in the other phase transition. So we measure, and when we wrote the paper, we speculate that it could be as exons from CRSBR are coupled, and if there's hybridization between MS2 and CRSBR, we expect some coupling between the exon in MS2 and the CRSBR, which can change this. And actually, at that time, it was only speculation from our side. Now there's a paper on archive. There's a model that they try to explain why you change the exon properties with this when you couple with the magnum. So they have a theory now. This is not published yet, but they have it. So we associate this change of trion by energy by this coupling of excitons with uncoherent magnum. It does not need to be coherent magnum. So more things. There are several unusual results. Another unusual results about these measurements of anisotropy. For CRSBR, it's the normal. It emits only in one on B direction. But for MS2 is isotropic material. So it should not change the intensity with the polarization. And when you combine both, if you measure on silicon oxide, it does not change. But if you combine with magnetic material, we can clearly see that it changed. And we tried to understand, at the beginning, Yaroslav Fabian said it's proximity effect, but after all, we think it is another effect. For what can be, what we plotted, it's the relative intensity of trion and exciton as function of this angle. I don't know if you know, but when the trion increases with doping, so if the relative intensity is changed, it means that the charge transfer is changed with the, so the charge transfer is anisotropic. Although it's on Z, it's anisotropic charge transfer. This is clear, and this is giving, and we can also see better when you apply field. So this can explain why this MS2 seems anisotropic. And another thing that happens, so this was previous published about CRSBR, that it is the exciton probe in the phase. When I measure on MS2 on CRSBR, what we see is that the intensity of MS2 is correlated to the phase transition. So the exciton intensity is probing the phase transition of CRSBR. And why? So this is how it changed. So it's when I have a spin flip, I have an abrupt change in the PL intensity. When I have a spin canting, I have a smooth change of the PL intensity. So it happens because of this, because the band gap change of CRSBR change with the phase. If the band gap of CRSBR is changed, you change the band alignment. If you change the band alignment, the amount of charge transfer is changed, but it's going to change, and the doping is changing. So you can use, it's just a very nice system that the phase transition modify the charge transfer, and you can probe this. And and this is evident because if you plot the relative intensity of exciton and trions, so if the trion intensity is stronger, which means that more doped, you can see that the relative intensity of trion and exciton change with the phase transition. This is more clear when we align the field with the z-axis, but in all cases it happens. It's more complicated to see here because we have valley effects that I will explain in the next slide. So we can use the PL intensity of exciton and trions to be a sensor of the phase transition. This is the message. But it's more complicated when you analyze apply magnetic field perpendicular, because we have this effect that I show, but I have also change of the valley properties. So you have this correlation with the phase transition here, but if you measure the Zimmer shift, I can extract the G factors of valley G factors, they are asymmetric. This is evidence that we have signatures of proximity effect. And this asymmetric proximity interaction, this was observed for 1 2D magnetic material previously. So you can see clearly, because if you put MS2 on silicon side, it's linear, one slope only, and here we have different slope. So different G factors. Here we extract, but it's just the values. Okay, but there are other, I don't know the time. Okay. So here there are a lot of things, but I can go faster. So this is a more recent work where I have investigated double S2 on CRSBR, which is interesting because when you have double S2, We have sharp emission peaks, which is providing system for single photon emitters. And it's more complicated, of course, and there are different effects, if I have time to show. So these sharp peaks have typical properties of localized excitons. So I will not explain in detail. This is well known. People use local strain to have these sharp peaks and to integrate with waveguide and photonic system to investigate single photon emitters for quantum technology. And the explanation of these sharp peaks is related to the local strain and hybridization of defects. People know this. I have investigated myself in other works, but I will not go in detail this because it's not the focus. What's interesting, there is also another exton in CRSBR that was discovered last year, more studied last year, which is the B exons, which involves a higher energy bands. And this B exon is different from A exon. Is less localized. A exon is more localized, and B exon is less localized. And this shift of energy when you do this probe, this phase transition, is much more important in this B exon. And this B exon is also more coupled with magnons. People have published, is this year, March 2025, they showed that's more coupled, that you can see clear oscillations of the energy of the exons. And they also show several things that are more important for this B exon as compared to A exons. So this is very nice work performed in a group of Venon. And why I say this? Because this B exon has an important role in my sample. I will show why very quickly. So this is the A exon and the B exon that change more. Here is 16 millielectron volts. Here is more or less 8 millielectron volts. And this is the color code map for perpendicular magnetic field. So the B is parallel to the CX. So we have clear changes here when we have phase transition, but we have a different result here for X and trion. You can see that that does not occur on the phase transition. And if you compare, this is very similar to the change of energy with magnetic field for the B exons. And I would go briefly because I don't have time. The main explanation is here. It's because I can change more, shift more this B exon, and it can have a resonance with exton, trion, and these sharp emission peaks. And there is an effect that people that works with optics very know well, that is energy transfer. This energy transfer effect, I think I have to show here. This effect can change the intensity of because you can have a resonance and you can transfer to another material, and there's several types. There is this Forster resonando, it's a dipole-dipole interaction, but there is also Dexter, which overlap of function, and this is well known for people that work with optics in different systems. So this explain this result that I observe here, but I will not have time to go in detail. Just more or less this. Why we didn't see before? Because MS2 is far from this B exon, and when you are in MS2, all emissions are around here. So if it's shifted with magnetic field, you can have resonant condition, which can give the result I show you. So we have also tried to measure time resolved, and we have shown that there's the times change, and which is consistent with this interpretation, but I'll not go in detail. And we also have observed this asymmetric magnetic proximity effect, that we have observed change of G factors for positive and negative fields. So I think I don't have time to go in detail with other results. The time is going on. No? Okay. So this is the same result for parallel. When the magnetic field is parallel to B, which is the z-axis. And this, we can see clear that the sharp peaks, when there is phase transition, increase the intensity, which means that this effect can also help for people that are interested in single photon emitters to improve emissions by using energy transfer. The difference is that it is the first time that you show that you can control energy transfer by magnetic field. Usually you cannot do this. It's just because of a specific properties of B exciton that shift and can have resonance. So, and after all, one thing before to finish, this energy transfer is anisotropic because CRSBR is an anisotropic. We can show that this effect occurs only when you detect a line to the BX. If it's not on the BX, it's not, you don't have this enhancement of intensity. So it's resonant energy transfer anisotropic because the CRSBR is anisotropic. This was observed before with black phosphorus that is anisotropic with another material. People have seen this. So this is expected, but we show this. So, and finally, there are different types of energy, resonant energy transfer, this forced coupling with dipole coupling, and you can observe only if the distance is lower than 10 nanometers. And there is another one that depends on overlap of wave function, so you need very close contact. And to test the nature, we have prepared a sample. We know Ingrid has prepared a sample where we put HBN between CSB, HBN very thin, and WS2 up. And we have controlled this thickness of HBN to be around 2 nanometers. So if it was forced resonant energy transfer, we should have this effect here. And we have removed the charge transfer effect, and we have removed energy transfer, which means it's probably more Dexter type. So you could have of course we do not prove, but it's consistent. And so finish. So I have shown that you can have surprise when you use material. There was one question that people that could ask, but I asked to myself, why you have this proximity effect if the magnetization is on the plane? So you should not observe, because you could not, we have observed splitting. I didn't show you splitting at zero, depending on the position that is more coupled, we have a splitting at zero field. And the main reason is because when you have the MOS2 that has quantization perpendicular and the magnetization on the plane, you can, by this interaction, you can tilt the magnetization of CRSBR. And also, so you can observe this. This was shown theoretically and experimentally in another work that I participate with the people from Regensburg, but I don't have time to show everything. So the conclusion is, so there are a lot of surprise, and you can use this TMD to be a sensors of magnetic properties, for example, or you can use CSB to change Valley and X properties of TMD. You can change trion bind energy, we can change linear polarization behavior, and you can observe anomalous change of PL intensity versus magnetic fields, and anomalous behavior PL versus temperature. So there's a lot of things to discover. You can have an asymmetric proximity interaction. Of course, I do not understand everything. I have explanation for a lot of things, but I cannot in detail. I do not understand. So there are other materials that can be combined and with CRSBR, which can be interesting to modify properties. So it's engineer. So magnet van der Waal had structured this hybrid structure with non-magnetic and magnetic material. Is a very interesting platform to change Valley and X properties of TMD for do different effects. So thank you very much for your attention. I hope you could understand something.
Thank you so much. So questions? Oh, yes, please.
Why don't you see any strain effects?
Is
Strain.
it's strain effect.
Because you put,
No, I didn't.
CSB.
No, but people have investigated CSB with strain. They control strain. They can see. This is interesting to do. I didn't.
Yeah, but
see.
I'm not talking about strain control.
Okay.
I'm talking about just. I mean, if you put a monolayer molybdenum diselenide on CSB, they probably don't match exactly. So there should be some. some distortion.
Yes, but I have no, I have no, if there's, I should look other, I'm not sure if there is something important. One thing that's important, I didn't say, but I didn't perform. I am aware from group from Munich that this effect that I have observed depends on the twist angle.
Yeah, okay.
And this I didn't explore yet.
That's a different story, of course.
Yes.
But let me put it differently. Like spectral lines you see, are they exactly the same as in non-deformed?
No, they are not. I think I didn't show here, but in the paper I have, if you put on silicon oxide, this is the question. But there are two things that can change. No, the position is different. On silicon oxide, because of two effects, the dielectric constants are different. I don't think it's a strain. I think it's dielectric constant of the materials are different. Yes, it's different. And in the paper, you can we put both together to see. I didn't put here, but it's true. It's true. It depends. Yes. And the trion band energy are similar, but it can change because of dielectric constant are different. Okay.
More questions?
Can you explain again what's the mechanism that pulls the magnetization out of the plane of the substrate?
So the magnetization from...
Yeah, so you mentioned...
with magnetic field, you mean?
No, without, or I don't know. So you have this magnetic substrate.
Okay, because there is a hybridization between the two materials. I'm not a theoretician. I didn't make the theory. There's the group of Yara Gobato that performed the. You only can evidence as experimental. We measure, and there's a split at B0, which means there is some component perpendicular, because only perpendicular magnetization can break the validation essence. But the main reason that they calculate details of calculation I don't have. They calculated and they show that this magnetization change because of this hybridization, because of proximity effect, because of this hybridization between the two layers. But details of calculation I can give you on the paper. It's the group of Yaroslav Fabian that...
maybe it's even related to the previous question. So the formation...
No, it's not this. No, it's proximity effect. Yes, a hybridization of the two layers is magnetic proximity effect, magnetic exchange proximity effect. This is even CRSBR. When you put another 2D magnet, there's another work is I don't know if CGT is another 2D magnet that has magnetization perpendicular. They put together at an interface they can see a tilt. And this is expected to be observed by magnetic proximity effect, but the calculation, detail of calculation, I don't know. I mean that, for example, I forgot the mind. If you have another 2D magnet with this CRSBR, if you want this magnetization is perpendicular and CRSBR is on the plane, you can tilt by interaction the magnetization of CRSBR, and this was shown. Is due to this proximity effect, this hybridization of materials.
So I guess what I meant is that so you have, due to hybridization, then you have the anisotropy of the material can change, and then you change. Maybe you have a small anisotropy out of plane or some. So you have some kind of easy axis.
Yes, maybe it is.
But I don't know.
Yes, so do I.
More questions? Maybe I have one. Probably it's a little bit related to that. So you grow, exfoliate the BSBs. What's the name? CSB on top of silicon, I believe.
Silicon oxide. Right. If it's bulk, it's okay. But if you have to exfoliate a few layers, better on HBN to avoid doping. Because silicon oxide is very...
Okay, but so my question is what will happen if you put on top of some magnetic material? You already gonna, I don't know, destroy or mess up with the magnetic ordering
No, you mean CSB? It happens that you can change the easy axis. You can change because it's a new system. You have this heterostructure. They interact. And you can change the magnetic properties on the interface. It's a very short effect because it's magnetic proximity effect. So only on few layers that you, if you have the bulk, you will not change. You change only close to the interface.
Yeah, makes sense. Makes sense. More questions? If don't, I think we can.
Thank you very much.
Move on. Thank you so
Thank
much.
you.
Thanks again. So I think now we'll have the next speaker, which is Lucas. I think is he right? Yeah.